Right. Good afternoon to today's presentation about the interferometer calibration survey for the BRAMS interferometer in Humain. Just a small overview, you saw it already before. We do have our transmitter here at DERB. We do have one interferometer here in Humain, and we have a new interferometer here in ECOTRON. For now, I did the calibration for the interferometer in Humain. The calibration for the interferometer in ECOTRON will follow soon. We do have here in both cases a classical Jones configuration. So we have a central antenna, 2 lambda towards east and 2 lambda towards south, one antenna, and 2.5 lambda towards west and north. To give you a small overview on the calibration procedure I did. So first, we start with the antenna measurements. So we have the real values, as you saw in the amplitude values, as you saw in Hervé's presentation. I then perform the Fourier transform over the sampling period. So in this case, 5,512 samples, 1 second. And then I'm performing the complex conjugate to get the interferometric phases of the antenna pairs I'm interested in. Then I take the emitter position, so I need a known position of a transmitter or an emitter. Do the GPS conversion from geodetic coordinates to local INO coordinates with the central antenna of the interferometer as a reference point. And then I do calculate the distance-based interferometric phase. So I have the emitter position, and I can then calculate the theoretical or distance-based phase shift by applying the known antenna positions here. And here we do have basically the emitter position or the wave vector. And then we get to the phase shift. So small schematic how it works. You have the planar wavefront coming from, for example, a drone. And then the planar wavefront is hitting one antenna before the other antenna. And you can here calculate then the difference, the phase difference between those two antennas. Then, after calculating the distance-based phase shift, we do the phase ambiguity resolution to actually know how much we need to unwrap the signal we measure with our antenna, because the measurements are always between -pi and pi. So we need to unwrap correctly the interferometric phase. And then we can perform this equation here to calculate the phase offset we are interested in. So we have discrepancies between the measurements, even unwrap, with the theoretical values due to system errors. And then in the end, we can calculate the calibrated phase that we see to identify where the object is. For the calibration campaign, we used the 3 drone flights. So we have the interferometer here, and the drone flights we started from here already several years ago. And then we flew to this point where we have azimuth values of around 39 degrees and elevation values of around 26 degrees. The second drone flight went down towards east. And we have an azimuth value of around 105 degree and elevation of around 90 degree. And the third drone flight goes towards west here with an azimuth value of 250 degree and elevation 27 degree. 0 degree azimuth is of course towards north, just for reference. So here I plotted the interferometric phase for the antenna pair, north antenna to central antenna. So I used for this calculations the interferometric phases between north antenna, central antenna south, west antenna south, central antenna, and central antenna east. And I show this plot because it's very interesting here for drone flight 1. So the first 20 data points here are for drone flight 1. And you can see here this typical wraparound we have because of the minus 180 to 180 phase sampling. And so we do have the measured phase here in kind of yellow. And you can see we are very much far away from the blue curve here. The blue curve here describes the theoretical, so the distance-based phase shift we would expect from this emitter position. And then we perform the phase ambiguity resolution, and we get very close to the expected values around the distance-based phase shift, but we still have, of course, the uncertainties here due to measurements. So we still have some additional effects, some errors. And we do this, of course, for several flights, for several antenna pairs. So we do have the antenna pair north-south, south-central, north-central, south-central, west-central, and east-central. And as you can see, already with the correct wraparound from a known emitter position, we get really close to the expected values we should or we want to have in theory. A little bit larger discrepancies here for between south and central antenna, but overall it's pretty close. So this leads to the phase offsets. So they are weighted, signal to noise ratio weighted. So we get for the north central antenna a phase offset of around minus 0.33 degree, south central minus 20.21 degree, west central 0.86 degree, and east central minus 5.17 degree. And I also show you here the maximum error. So I thought it would be important or interesting in this case, how much, what's the maximum phase error we get during those 110 data points compared to the weighted signal to noise ratio values. And as you can see, we have here values of plus minus 25 degrees in the phase difference for north central, around 19 degrees for south central, 40 degrees for west central, and 27 degrees for east central. So this still gives a little bit of a variety, or we were hoping to get values that are smaller in the maximum error, but we also need to keep in mind we have low elevations. So as I showed you before, elevation angles are between 19 and 26 degrees. So I think it's still pretty good. So then here is the plot for the direction finding based on the known emitter position. So we know how much we need to wrap around. And what I plotted here is, first of all, those red curves here. Those are the solutions for azimuth and elevation for the non-calibrated interferometer. So you can see we pretty much rubbish. What we down have here in green, that is the azimuth and elevation from the GPS data. And also the calculated here in yellow is the azimuth and elevation from the distance-based phase shift calculation. And we do have the calibrated results here as well, using the phase differences from the calibrated interferometer. And now having a little bit closer look on the plot before here. So, I mean, we have here very large differences, so you don't see much. If we now look a little bit closer, we can see for the elevation, of course, the distance-based and the GPS-based elevation calculation, they are pretty much identical. There's a small offset I think half a degree or so. I mean, also uncertainties, computational uncertainties. And from the calibrated interferometer, here this yellow curve here, we see we have a offset of around up to 6 degrees. So we are pretty good for an elevation. So this is for drone flight 1, the example. So for an elevation of 26 degree, we have an uncertainty or an error of up to 6 degree here for the elevation. And if we have a look at the azimuth angles over the 20 data points, we can see we have here also a uncertainty of around or an error of around up to 5 degrees here, a little bit less, which shows a pretty good agreement. But so to summarize and to make a conclusion, the phase ambiguity resolution is very important to perform the angle of arrival analysis. The drone calibration showed a small offset. The elevation angles are small as well, so kind of expecting some error here. But still the angle of arrival estimation based on a known emitter position, so the correct phase ambiguity resolution, is in good agreement with the expected GPS-based emitter position. And additionally, I did not put error bars here for the GPS analysis. We are expecting here an accuracy of ±1 meter of the GPS data. Coming to an outlook, so I'm currently also working on the calibration using ADS-B data. So ADS-B data is data from aircraft positions. This is an example of a spectrogram, and we have this noise thingy here, and this is actually a plane we see with the interferometer or with the receiver stations. And from this data, I can then reconstruct the or I can perform the angle of arrival analysis. Of course, I need to know the correct plane at this position. I will also do this for the second interferometer in ECOTRON. And then we are planning to do regular calibrations to check the system condition and to also correct for the phase in case there's a restart of the system. Either manually or automated, I need to see. It's probably gonna be manually. I want to do something else as well. And I'm about to finish the direction finding algorithm with the correct phase ambiguity resolution. And to do that, I will probably need to switch from the real phase angles I'm also used here to the complex phases. I got some nice feedback already at the Meteor workshop. So this is probably gonna solve a lot. And I guess maybe beginning of October, this problem will be solved. Thanks a lot.
Thank you, Johanna Sebastian. So this is really nice to see that, well, when you do away the unknowns there and you do that, it gets much better when you detect for, well, the several multiples of the phase that you now know. Are there any questions in the room? Yes, Johan?
So what was your SNR on the reception from the drone? Because I would have expected much smaller residuals.
So if I remember correctly, the signal to noise ratios were about between 6 and 12 decibel above the noise level.
Okay, so quite low.
Yeah.
Thanks, Daniel. Any other question? Are there any questions online? It doesn't seem so. So if not, then let's thank the speaker again.